Yes, I can still see your screen, and it's now 1:30, so I think it's time to start on your talk. So our next speak will be by Kristof, and I'm sorry, I'm not sure I'm going to pronounce it correctly. Huszar, is that right?
Yes.
Okay, Kristof Huszar on the pathwidth, that's hard to say, of hyperbolic 3-manifolds.
Yes. Thanks a lot. All right, so I hope that you can hear me well.
Yes, we can hear you.
Yes, okay.
Anyway.
So thanks a lot for the opportunity. All right. Thanks a lot for the opportunity of giving this talk today. So yes, indeed, I will be talking about the pathwidth of hyperbolic 3-manifolds, but I will also be talking about the context of this research that stems from my PhD. And as such, what I will be talking about in the next 20 minutes or so is to a great extent joint work with my advisors, Jonathan Spreer at the University of Sydney and Uli Wagner at IST Austria. So to set the ground, I would like to talk about some basic definitions. In particular, I would like to introduce the main objects of interest in this talk, compact and orientable 3-manifolds, in a way that they mostly appear in a computational setting. And this is the structure of a triangulation. So according to this classical theorem by Moise, every 3-manifold has a triangulation, which is a collection of finitely many tetrahedra glued together along triangular faces. So here is an example of a triangulation of two tetrahedra. And what I also allow in this setting that two pairs of triangular faces on the same pair of tetrahedra are identified. And I even allow that two triangles on the very same tetrahedron are identified with each other. So it's more flexible than a simplicial complex. Nevertheless, you can always get a simplicial complex by taking at most two barycentric subdivisions, if you wish so. In what follows, it will often be useful to forget the exact way the tetrahedra are glued together and to focus only on the pairs of tetrahedra that are identified or that are glued together with each other. And to capture these incidences, the dual graph, also known as the dual one skeleton of the triangulation, is a very useful object. So here we take a vertex for each tetrahedron of the triangulation and an edge for each of the face gluings. And by construction, this will be a graph, possibly with multiple edges and loop edges with vertex valency at most 4. What I would like to mention that this way of looking at 3-dimensional manifolds is quite efficient in the sense that more than 13,000 topologically distinct 3-manifolds can be triangulated with 11 tetrahedra or less. Now, the broad context of our work is the algorithmic study of 3-manifolds. And well, it's a very basic fact that any manifold that can be triangulated in infinitely many combinatorially distinct ways. In particular, the homeomorphism problem is a non-trivial problem. So what is this problem? It is a decision problem that asks to algorithmically decide whether two given triangulations of D-manifolds are homeomorphic or not. And the difficulty of this problem is strikingly different across the dimensions. In 2 dimensions, the problem is quite easy because there is an easily computable invariant, the Euler characteristic, that provides a complete classification of closed orientable surfaces. At the same time, if the dimension is at least 4, the problem becomes undecidable, and this has the reasons for this is rooted in algebra. In particular, it follows from the undecidability of the group triviality problem. So staying in dimension 3, the realm of this talk, the homeomorphism problem has a solution. However, all known solutions, they rely on geometrization, And as such, the proof and the algorithm itself is very complicated. It exists at this point only at the theoretical level, and its complexity is also quite elusive. So there is a lot still to be understood here. And therefore, in practice, if you would like to distinguish between two given triangulations of three manifolds, either you guess that they encode homeomorphic manifolds, and then you might want to try to relate them by a sequence of so-called Pachner moves, or if you believe that the two triangulations are distinct, homeomorphically distinct, then you might want to try to distinguish them via computable invariants. And I would like to follow up on this direction. So here, when you're talking about computable invariants, even though not only you cannot guarantee a complete solution to the homeomorphism problem, meaning that if two triangulations have the same value for a certain invariant, they can still be distinct. However, most of the invariants in three-manifold theory that have the power to distinguish between large classes of three manifolds are very hard to compute. And therefore, in recent years, there has been a growing effort to find algorithms for computing these invariants that somehow take into account the structure of the input triangulation, by which I mean that you want to understand the complexity of these algorithms, not only in terms of the size of the input, which is here denoted by n, but also by means of other structural parameters. In this slide, it is one such parameter is exemplified as being the treewidth of the dual graph. So I will discuss this quantity very soon. At this point, I would like to draw your attention to the central column of this table and observe that the size of the triangulation always appears as a linear factor, and all the ugliness is hidden in the other factors. In particular, if you assume the treewidth of your input triangulation to be fixed or bounded, then all of these algorithms are running in linear time in n. And the presence of these algorithms has motivated a guiding question for us, namely, given a three-dimensional manifold M, how small can the treewidth of the dual graph of any triangulation of M be? And these problems that I have shown for you in this chart, this table, these are problems and algorithms about three-dimensional manifolds. Nevertheless, there are similar developments in recent years also in, well, the closely related theory of knots. Here you can see a link diagram as a four-valent graph, and you can consider its treewidth. And several link invariants have been shown to be fixed parameter tractable in the treewidth of the link diagram, several well-known knot polynomials and quantum invariants as well. And that also begs the question whether there exists a universal constant such that every link L has a diagram D with treewidth bounded by this constant. And it turns out that this is not the case, as it has been shown by Arnaud de Mesme, Jessica Purcell, Saul Schleimer, and Eric Sedgwick a few years ago. They established a very interesting relationship between the knot and the treewidth of any diagram of the knot. In particular, this result, which I at this point I don't have time to talk more about, it establishes a relationship between the topology and the combinatorics of knots, and it in particular implies that certain families of knots, for example torus knots, cannot have diagrams with small treewidth. I would also like to mention, as following up on Colin's talk, who mentioned SnapPy during his talk, that there exists another software for low-dimensional topology called Regina that contains implementations of several of the aforementioned FPT algorithms, and is also a very useful tool for research in low-dimensional topology. If you're interested, I recommend you to check it out. All right, so now I would like to talk about the treewidth and the pathwidth of graphs and tree-manifolds in a slightly more concrete terms. So the treewidth of a graph is a parameter that quantifies the similarity of the graph to any tree, as the name suggests. And the definition itself is a bit technical. I have a backup slide about it if you are interested. Here I would like to illustrate this notion via examples. So as one might expect, the treewidth of a tree is 1, and the treewidth of the complete graph on n vertices is n-1, and you can get actually everything in between. And similarly for the pathwidth, the pathwidth of the definition of pathwidth is very similar. It quantifies the similarity of the graph to any path. Now here, an interesting example is that while the grid and the complete graph have the same treewidth and pathwidth, the example on the left, the complete binary tree, shows that trees can have arbitrary large pathwidth. So how do these quantities, parameters for graphs, become invariants of manifolds? Well, oh yes. So before that, what I want to mention is that these notions, the pathwidth and the treewidth, have been key concepts in graph minor theory. They are also very important in parameterized complexity theory. And these are not the only width parameters for graphs. There is an entire zoo of such parameters that capture the structure of graphs in one way or another. And now I would like to define the treewidth and the pathwidth of a 3-manifold M, of a compact 3-manifold M, simply by minimizing their values over all possible triangulations, over all possible dual graphs the manifold can admit. And these definitions, these are motivated by this guiding question that I posed in one of the previous slides. And so our goal in this research project has been to develop an understanding, a quantitative understanding between the treewidth and pathwidth of a 3-manifold and its classical topological invariants. And so in the second half of my talk, I would like to provide an overview of such results, in particular the one also mentioned in the title. So first I would like to cite some results that relate the Heegaard genus to these parameters. A few years ago, with my PhD advisors Jonathan Spreer and Uli Wagner, we managed to show that if M is a closed, orientable, irreducible, and non-Haken 3-manifold, then its Heegaard genus always gives a lower bound on its treewidth by means of the following inequality. And when we combine this work with earlier work of Egel, who showed that there exist exactly such 3-dimensional manifolds with arbitrary large Heegaard genus, as a corollary, we get a result that is analogous in fashion to, or similar in fashion to, the one I mentioned about knots by Demesme and his colleagues, that there exist, in fact, 3-manifolds with arbitrary large treewidth, meaning that for such 3-manifolds, no triangulation can have a dual graph of small treewidth. In subsequent work with Spreer, we were able to show a converse result, namely that the Heegaard genus always gives an upper bound on the pathwidth, which by definition gives an upper bound on the treewidth. And as a corollary, it follows that for non-Haken manifolds, the pathwidth and the treewidth and the Heegaard genus are always within a constant factor. For hyperbolic manifolds, which were discussed by Colin, so first of all, we have the Mostov rigidity theorem, from which follows that geometric properties of hyperbolic manifolds are topological invariants. In particular, as mentioned by Colin, the volume of a hyperbolic 3-manifold is a topological invariant. And as such, it can be related to the treewidth, as it was done by Clément Machia and Jessica Purcell a few years ago, where they showed that there exists a universal constant C, such that for every closed hyperbolic 3-manifold M, the treewidth of the manifold is upper bounded by constant times the volume. And what I was able to show that this inequality actually even holds for the pathwidth of the manifold, which could a priori be much larger than the treewidth. So for the rest of the talk, for the remaining 5 plus epsilon minutes, I would like to give a brief overview of the toolbox and outline the proof of this theorem. So I have mentioned several viewpoints one might look at three-dimensional manifolds, and these results, they all aim to establish a relationship between these different viewpoints in a quantitative way. So between triangulations, Heegaard splittings, in case of geometric manifolds, properties of the thick-thin decomposition, and quantitative relationships, inequalities between associated invariants to these different structures. And to achieve this, luckily, we don't need to start from scratch. There exists powerful machinery to establish bridges between these different points of view, in particular in a quantitative way. So for instance, generalized Heegaard splittings, they provide us an interface for turning various decompositions of three manifolds into Heegaard splittings. Layered triangulations, for our purposes, they are an interface for turning Heegaard splittings into nice triangulations of three manifolds. And it is also important in several of these works that the thick part in a thick-thin decomposition of a hyperbolic manifold can be triangulated in a very nicely controlled way, where the number of tetrahedra in the thick part is bounded by the volume. So very briefly, I would like to say a few words about generalized Heegaard splittings. So probably all of you or many of you know classical Heegaard splittings, where a three-manifold is built by gluing together two identical handle bodies. In case of a generalized Heegaard splitting, a three-manifold is built by gluing together several pairs of compression bodies following certain rules. So what is a compression body? A compression body is similar to a handle body, but it can be hollow. In particular, the construction of a compression body starts by taking a surface, possibly disconnected, then thickening it up by multiplying with the interval, and then attaching some solid one handles, and potentially filling in some of the two-sphere boundary components. And this appears to be somehow a bit arbitrary, but it turns out that this is a very nice definition. And when you consider essentially arbitrary decompositions of three manifolds into submanifolds that intersect nicely along surfaces, then you can always turn this into a generalized Heegaard splitting, where for each of these submanifolds you consider a Heegaard splitting using compression bodies. Certain splittings are not allowed. This circular splittings here, we don't want to consider them. And there is also a very nice language in terms of so-called fork complexes to describe a generalized Heegaard splitting and to capture its connectivity properties. And one of the main strengths of generalized Heegaard splittings lies in the fact that they can be manipulated in various ways by so-called untelescoping them, amalgamation. By amalgamation, we can recover a classical Heegaard splitting from a generalized one, and so on and so forth. And therefore, they are very useful in this context, as we will see in a moment. Yes, it's just a historic remark that the generalized Heegaard splittings for three manifolds were originally also inspired by the thin position for knots in the three-sphere. Layered triangulations. Here I just have a picture of a construction. Here what happens is that essentially you construct a triangulation in a layering fashion, where where a layering is just gluing a tetrahedron as a procedure where you glue the next tetrahedron on the boundary of the existing partial triangulation in the most natural way you can imagine, which is also shown on the picture. And Jacob and Rubinstein have developed a theory for such triangulations. In particular, they have shown that every 3-manifold admits such a layered triangulation, and they can really be thought as triangulations of Heegaard splittings. So I would like to conclude the talk by an outline of the proof of theorem 3, which here I made a typo. I noticed I wrote theorem 5. Nevertheless, that's the same theorem. So I would like to prove that there exists a universal constant C such that for every closed hyperbolic 3-manifold M, the path width is upper bounded by this constant times the volume. And here is a pictorial outline of the proof. So initially we start with a hyperbolic 3-manifold M with a given volume. I would like to find the triangulation for this 3-manifold M so that the path width of the dual graph of this triangulation is upper bounded by constant times the volume of M. And in the very first step, we consider a thick-thin decomposition. Here the dark gray part, which are illustrated as spikes on this schematic, they are essentially neighborhoods of short geodesics. They are topologically just solid tori, and the thick part, which is denoted by M1, is the one where all the complications occur. However, by work of Jorgensen and Thurston and Kobayashi and Rick, it can be triangulated in a controlled manner. Now, we don't use this work to directly proceed to a triangulation, but we can make use of this theory to first construct a generalized Heegaard splitting associated with this thick-thin decomposition, where the surface S1 has genus bounded above in terms of the volume, and all the other surfaces Si, they will have genus 1. And the number of these smaller surfaces Si is also bounded in terms of the volume linearly. And now in the subsequent step, we amalgamate this generalized Heegaard splitting into a classical one, following the work of Schultens and Bachmann and others. And we can conclude that the genus of this classical Heegaard splitting is still bounded above by some constant times the volume. And in the final step, we make use of the work of Jacob and Rubinstein, and we deduce that we can now provide a layered triangulation of this manifold, where actually the path width is bounded above in terms of the volume, in a way as it is stated by theorem 5. And I would like to conclude with this note, and I thank you for your attention.
Okay, let's all thank Kristof. And do we have any questions? Feel free to unmute yourself and ask if you have a question.
I maybe have just a naive question about what you consider a tree in this context. I suppose you allow two different paths from one node to another, right? So you're allowed such cycles?
I'm sorry, I'm not entirely sure that I understand.
So when you showed a picture of a tree, you showed a picture of something that I'm not sure all my computer science friends would call a tree.
Oh, yes.
But I suppose you cannot ever have leaves. You cannot ever have true leaves in this tree, right?
You mean this picture?
Yes. So you're permitting these kind of loops, right?
So no, so here, yes, but so this is yes. So why do the loops appear at the first place? Is because we allow loops in the triangulation simply because we allow triangles on the same tetrahedron to be identified with each other when we are considering triangulations. So here, what I really mean by a tree is that once you erase all multiple edges and all loop edges, the remaining part of the graph should be a tree. So in this sense, I understand the trees in this slightly more general sense.
Okay.
Of course, you can also have leaves and you can have a normal tree if you consider appropriate triangulation.
Okay, I'm having a hard time imagining such a triangulation, but if you say
well, if you give up on your manifold to be closed,
okay, yes, then one can.
Then yeah. But for, of course, for closed tree manifolds, you will always have yes, exactly. You cannot have conventional leaves.
Okay, very good. I think I understand now.
Thanks for your question.
Okay, any other questions? Okay, if not, let's thank Kristof again. And the next talk will be at 2:30 Central US time and about half an hour from now. So I think that's right. Double check the schedule. Yes, at 2:30. And so everybody feel free to